So today, just carrying on with what we did yesterday, talking about finding volume using washers. So remember, it's pi times the big radius squared minus small radius squared times the thickness or the height. And that's the volume of a washer. Setting that up with an integral, we're just adding up lots of washers to find the exact volume. So we're doing the definite integral from a to b of pi, and remember that pi could be inside or outside. Big radius squared minus little radius squared times dx. This is if we're going around the x-axis. Remember, if it's going around the x-axis, that means it's going to be a dx cut for discs and washers. If it goes around a y-axis, it's going to be a dy cut, meaning everything in there is going to be in terms of y. Now, number one is actually one we kind of maybe finished on yesterday. I don't know if we got to this in class, but we didn't. I know we didn't finish it, even if we got to it. So let's take a look at number one. It says the region bounded by the graph of y equals square root of x, y equals 0, x equals 1, and x equals 4. So let's sketch that graph. Square root of x, we know, is just sideways, half of a sideways parabola. Y equals 0 would just be our x-axis. X equals 1 is a vertical line. X equals 4 is a vertical line. So this is the region that we're dealing with. And we're told that it's revolved about the y-axis. So we're going around the y-axis. What kind of cut does that give us then? Or what kind of cut do we need to use? dy, right? We just talked about that. It's got to be a dy cut. Now, looking at this shaded region, does that look like a dy cut? No. If I asked you to just find the area of that, the best way would be using dx cut. So it makes things a little bit more complicated when we have to use a dy cut. There is something we'll learn later on, next section, shells, finding volumes using shells. That would make this a little bit easier, but for now, we don't know that. So we have to do it using washers. And to do that, we're going to have to break this up into a couple parts, kind of like we did it with one of the areas on our starter yesterday. Because if we're looking at a dy cut up here, towards the top, we can look at a rectangle with a dy cut. On the right side, it goes through this line, or the right side touches this line, x equals 4. Left side is right here on the sideways parabola, or the square root function. But if you go lower, like down here, the right side is still that line x equals 4, but the left side is x equals 1. It's not one function that's always to the left, or one function that's always to the right of the other one. So we have to break this into two parts. Where do we break it up? Where does it change from line minus square root function to line minus line? At the intersection right here, right? So if we look at where those two intersect, I'm going to draw a line, horizontal line over here. And we're going to break this into two parts. That doesn't work. Alright, so we're going to look at this section down here, along with this section up here. As we're breaking it up into two parts. So basically we're going to find what volume does this shape make when it rotates around the y-axis, and what volume does this shape make when it rotates around the y-axis, and add those up. So I'm going to kind of represent that up here. So we're going to take this shape, rotate it around, plus what we get when we take the rectangle and rotate it around. So let's look at this portion first. Remember, we were talking about drawings here. We've got this horizontal rectangle, and not that this is a big deal now, but once we start dealing with shells also, it's going to help you to visualize what we're dealing with. If we spin this around, we see we've got a washer. And the little radius always goes from the axis of revolution to the closest function, or the inside of that rectangle. So up here, that would be here. From the axis of revolution to the closer function, or like the inside of the rectangle, or the part that's closer to the axis of revolution. Then the biggest, or the big radius, goes from the axis of revolution to the farthest function, or the other side of that rectangle. So our little radius, that's an x value, right? It's a horizontal distance, so it's going to be the x value of this square root function. But we can't leave it in terms of x. It's a dy cut, which means everything has to be in terms of y. So we need to determine what's x equal to on that square root function. So if we were to solve this equation for x, what would we get? Y squared. Right? So really our little radius is going to be y squared, because we need it in terms of y, since it's a dy cut. Our big radius is going to be the x value of this line. Oops, I don't know why I drew that again. It's already up here. Our big radius is right here. Right? So it's the x value of that line, but what's the x value of that line always going to be? Right, so we have the x value of the line. This was the x value of the square root function. So we've got little radius, big radius. We can set up our integral. So for this one, for this portion of it, we're going to have pi times the definite integral from the lowest y value to the highest y value. We'll figure that out in just a second. Of the big radius squared, so that's just 4 squared, minus the little radius squared, so we've got y squared squared dy. So we need the lowest y value, biggest y value for this definite integral. Well, the lowest y value happens right here where this intersection happens. So we need to figure out where do those two graphs intersect. That's square root of x and x equals 1. So we have a system of two equations that we're dealing with. We can use substitution. If we put 1 in for x, y is going to be square root of 1, which is just 1. So this points at 1, 1. That means our smallest y value is 1. Biggest y value is going to be up here where these two graphs intersect. So still square root of x. We want to know where does that intersect with x equals 4. So we can substitute that in. Y equals square root of 4. We get 2. So this point is at 4, 2. So our biggest y value is 2. Now we need to figure out little radius and big radius for this blue region that's going to get spun around the x-axis. So our little radius goes from the axis of revolution to the inside function, and then our big radius goes from the axis of revolution to that outside function. So our little radius, what's that always going to be? The little radius. No matter where that rectangle is, if we move it up or down, that little radius is always 1. Alright, big radius, always going to be 4. Always goes to that line, x equals 4. So for this shape, it's pretty simple. We've got pi times definite integral, we'll figure out the a and b in a second, of big radius squared, so 4 squared, minus little radius squared, 1 squared, dy. So what's our lowest y value? So looking at that blue shape, 0 is the lowest part. Highest part is 1. Now we could put those in our calculator, but before we do that, I would simplify things a little bit, and we're not going to bother putting in the calculator today. I just want to have it set up. So we have pi times definite integral from 1 to 2 of 16 minus y to the 4th. So it helps to do that so you're not having so many parentheses, so many things to type in. Plus pi times definite integral from 0 to 1. We've got 16 minus 1, so that's just 15 dy. And these are also ones that would not be too difficult to do by hand, but for now, for today's notes, we're just going to go ahead and set up the integral. We're not going to evaluate.